Welcome again to the unit circle. There is peace and serenity in the unit circle. Today we're going to talk about our last thing for the school year, graphing sine and cosine. This is the last thing you need to know for your final test this week. I did talk to you guys about permutations and combinatorials getting cut. And what I decided to do, because I really hyped up permutations and combinatorials, and I don't want to let you guys down by cutting that content. So what I decided to do is, next week I'm going to do a series of bonus lectures on permutations and combinatorials with an assignment or two, and you are welcome to do those for extra credit. Okay, so I'm not really big on extra credit, but I don't want to assign something that other teachers aren't and giving you more, but I also don't want to deprive you of this experience, and they are an experience to be had. Okay, all right, so let's begin by taking a look at this unit circle here. I want to talk about how, if you recall from our previous conversation, and I say conversation, but it's just a crazy old man talking to himself here. We had talked about how, let's talk about cosine first, okay? So I'm going to talk about cosine. And I talked about how as cosine goes around this, as our line here goes around this circle, cosine changes, right? When our line is right here going horizontally, cosine is 1. And then when the line is straight up and down, cosine is 0. And when we are back over here, straight over here, cosine is -1. And when cosine is down here, it's 0 again, because cosine is the x component of our triangle. And so when our line is completely horizontal like this, and the hypotenuse is 1, this horizontal is the hypotenuse, and therefore the hypotenuse length is also the horizontal, which is 1, right? And here it's -1, it's going back instead of forward. And on these 2 points right here, when our line is straight up and straight down, it's straight. Cosine is 0 because there is no x component to these, right? It's purely a y component. So one thing we talked about before was how the unit circle, being a circle, repeats itself, right? We can keep going around and around here, and we'll get the same values over and over again. So this point right here, one of its values is 0. This is 0 degrees. But then you also know this is 360 degrees, and it's also 720 degrees, and it's also 1080 degrees, and it's also 1440 degrees. Hopefully I did all that mental math right. So all of these, when our unit circle is any of these, we do cosine of any of these, right? Cosine of any of these is equal to 1, because it's all talking about this same point right here, the purely horizontal line. So what that means is if we graph cosine for all degrees, we get repetition, okay? We start at 1, then go to 0, then to -1, 0, 1, 0, -1, 0, 1, okay? And so what that looks like in practice, that's right. Here's I'll move this here. Y equals cosine of x, okay? So that's what it looks like. So this might look crazy to you, but it's really simple. It's just the unit circle being repeated over and over and over again, okay? So here's my, this is my degrees, okay, in radians. Notice how this is in radians in here, pi over 3, 2 pi over 3 pi. You can change that in decimals by clicking on graph settings up here. And you can click radians or degrees. Well, no, it wasn't. Oh, step. I put, for my step, I put pi. Okay, if I take that out, I go back to the usual numbers. And this isn't as great because you can see here, like, here's 0, and like, what is this value right here? You know, if you click on it, it's pi over 2, but you can't tell just by looking at it, right? You can't tell what this is over here just by looking at it. So if you change that to pi, and then you just type pi, and it does it. It changes the scale rate here to radians in a sense, so you can look at it. If you click on I think it's better to look at these in radians than degrees, because degrees you need to get to 90, right? So if I like the degrees are much bigger than radians. So if I click degrees, notice how this is like this, because you have to zoom way out to see this is the curve. You can see the curve going up and then hitting 0 again. So I really recommend keeping this in radians. Oh, look at that, that's cute. Okay. And let's talk about the features of this graph. Did I look at this before? Maybe it was like that. Maybe like that. This is better, I think. Okay, this is perfect. So what do we know about cosine? When my degree, actually I'm going to do some drawing here. So I'll delete the other stuff that I was doing. Okay, so what is cosine? If I do cosine of 0, right, that's 1. So here's 0. So here's at 0 I have cosine. At cosine of 0 I have 1. Oh, I don't really want to cover up the number 1. It's like your only visual reference. I have this point 1. Okay. And then what's another important value? I told you before, and you should know by now, that cosine of 90 degrees, which is the same thing as pi over 2, right? Cosine of pi over 2 is 0. That's the, that's the straight up vertical up and down, right? That's pi over 2. Same thing as 90 degrees right here. So we expect that I do cosine of pi over 2, it's 0. Well, here's pi over 2, and notice my value is 0. Then as I do cosine of pi, you guys know that's -1, right? 'Cause it's going back on the unit circle. And look, when it's pi, I get -1. And as we keep going, right, I get cosine of 3 pi over 2, which gives me 0 again, because that's pointing down the unit circle. And at this point, after we point down the unit circle, we're back pointing right again, right? We're at 2 pi. And 2 pi is the same thing as 0. So what's cosine of 2 pi going to be? It's going to be 1 again. So we're back up here. So in effect, what happens when you graph cosine is you just get these repeating loops over and over and over again. And this is used in anything that undergoes repetitive motion called oscillation. So for example, when engineers are working with turbines, engines, and things like that that have turning parts that are rotating over and over again, these functions, which are called sinusoidal functions, if it repeats over and over again like this, we call it a sinusoidal function. These sinusoidal functions accurately depict those kinds of things. Or think of like a spring. You know, if you take a spring and you compact it down and let go and it goes and it goes up and down over and over again, that's that oscillation is going to be captured by this as well. Okay, and in fact, you know, I've had test questions like that. So that's the essence of what we're doing. So if this is cosine, what's sine like? Well, let's turn off cosine and turn on sine. And looking at that, you might say that looks like the same thing. It's not the same thing. It's very similar, right? But not the same thing. If I turn on both, you can see there's a difference between them. What's the difference? Well, sine has 1 and 0 values at the opposite place that cosine does, right? When we have 0 degrees, there's no y component. So if there's no y component, our sine of 0 is 0, right? So that's why this point right here exists. And then when we do sine of pi over 2, that's our 90 degrees, right? That's straight up and down, that's 1. Because it's completely a vertical component. So at pi over 2, that's where we get 1. Okay? And it continues, sine of pi is 0. That's why we have this 0 right here. And then sine of 3 pi over 2, that's pointing straight down, and that's -1 right here. Okay? So I'm talking right now like you've mastered the unit circle from last week. If you didn't, it might be good to go back and review that a little bit if you're totally lost right now. But this is assuming that you understand that concept that we've gone over in the past couple weeks, okay? So that's all we're doing with sine and cosine and graphing them. It's pretty easy. Now, let's go to the notes. And we're continuing this week with the same thing. You only have 1 assignment due plus the test this week, okay? I'll have the guided notes posted. Where do I have this? Here we go. Okay. So let's talk about a couple things that are important, okay? Well, we talked about them being cyclical, okay? I gave you a graph that looks kind of like this, but was way better. And we're going to talk about 2 periods of terminology now, the period and the amplitude, okay? And the period is, when we say the length of a cycle, that means the amount of, I want to say time, but it's how many units have to pass before we are repeating ourselves, okay? So if I go to cosine, I just like cosine better than sine. I don't know. I like C more than S, I guess. Roman's really struggling with this. The whole C can make a S sound sometimes. He tends to think that anything with a like if I say this is a snake, I'll be like, well, what does that start with? He'll be like, oh, C, because it's a S sound. I'm like, God, English, you are such a piece of crap language. Anyway. So, the other day, he can spell his name now. That's really good. And my wife, his penmanship's getting really good too. My wife wrote down the word kaiju, and he wrote kaiju down very well. Okay, so let's take a look at this. So what do we notice on this graph? Okay, it's repeating, obviously. And when is it repeating? It repeats. We got this point right here at 1, right? And it goes from 1 to -1, and then back to 1. Okay? Now we're back at our start. Okay, and after this, it's gonna go, oh wait, that won't follow. Well, that was not smart. Yeah, it was just dumb of me. Okay, let's zoom a little bit for a different perspective. Okay, let's try this again. So from 0 to 2 pi, that's how long it takes for this to repeat and be back at 1. And then the next time it's back at 1 is at 4 pi. So from 2 pi to 4 pi, that's how long it takes to repeat. What's the distance on the x-axis between 0 and 2 pi? It's 2 pi. That's our distance. What's our distance from 2 pi to 4 pi? It's 2 pi, okay? So this right here, this is our period. That's what a period is. A period is how long it takes for something to repeat. Rather, just the sinusoidal function to repeat when it's graphed, okay? So what that means is, you'll notice cosine has a 2 pi period, but sine also has a 2 pi period, right? Here's my peak at pi over 2, and then 2 pi later, we're at 5 pi over 2. One thing I recommend doing when you're looking for period on these, don't use the zeros, okay? Because you might say, oh, 0, 0. But this is not repeating, right? This is the opposite side 0. If we go from 0, this is the other 0 right here. These are the two zeros. I recommend not doing it because it's more confusing. It's better to go from peak to peak or from trough to trough, okay? Otherwise, you might get confused by the zeros. But if you do, make sure it's a declining 0, or inclining 0, inclining 0, if you're comparing the zeros instead of the peaks, okay? Either way is fine. So both sine and cosine, there we go. So for period, notice here's sine, and here's the graph, has a period of 2 pi. Cosine has a period of 2 pi. So every 2 pi, it's going to repeat itself. In degrees, that means every 360 degrees it repeats itself. But when graphing, like I said, we tend to look at radians instead of degrees, just because otherwise, you're having to graph every 360 on the x-axis for your cycle, like I showed you when I changed the axes, and that's ugly, right? That's just gross. Okay, so and the way this defines amplitude is half the distance between the minimum and maximum values. That's one way to define it, okay? The way I like to think of okay, first, let's talk about an intuitive way to think of it that isn't always correct, okay? An intuitive way to think about this is amplitude is the highest value possible, okay? So what's my highest value possible? 1. That's my amplitude, okay? What else for sine? What's my amplitude? Highest value possible? 1. So if we look here, notice in the notes, the amplitude is 1 and 1. Now that's not actually how you figure it out, but it's something useful. That's the intuition behind it. Why we care about amplitude? We want to know, like, how high is this bouncing up? But really, what amplitude is doing is it's measuring from, there's something called the midline. Okay, this is the midline on these graphs. And the amplitude is asking what's the distance from this middle point on the graph to the peak. Okay. So what's that distance from 0 to 1? It's 1. So that's why the amplitude is 1 here. And the reason there's a difference, you might say, well, it's the same thing. But there is a difference here, right? If I make this cosine of x plus 1, right? Well, if you look at this, by the first definition where I said, well, what's the height? I would say the amplitude is 2. But that's not correct. The amplitude is still 1, right? Because this is my midline now. And so what's my distance here? It's 1. Now another way you can do it is you can take the highest point and the lowest point and take this distance between them and average it, right? And that's what this is doing right here when it says half the distance between the minimum and maximum values. So another way you can find amplitude is by taking this top point, which is 2, okay, adding it to the lowest point, 0, and then dividing by 2, averaging them, which is 1. And that gets us our 1 still, right? And this works if I do this like plus 4, for example, okay? What's my distance between these two? 5, 3. So I have 5 minus 3 divided by 2, which is still 1, okay? And if I make my midline right here, you know, it still looks like 1. So it doesn't matter where it is. You can use different techniques to find that amplitude, okay? So that covers amplitude, that covers period. Now let's start talking about, I don't know if we want to call this standard form or not. I don't know if that's technically correct, but this formula, y equals a times sine of b theta. That's a pretty big jump, you might say, but we're not going that far, right? Y equals we'll get this, y equals cosine x. That's like y, can I do theta? Yeah, okay, look at that, y equals let's stick to theta then, okay? I'm just changing to x to theta, so it looks like this formula right here, okay? So it's a little less visually confusing. Theta is just x, okay? It's just, theta is used for angles, typically. So don't be alarmed by that. So what do I have? What's different here? I have an A here, and I have a B here. And I want you to have an intuitive understanding of what these do. Amplitude is caused by A. Period is caused by B. I think the period's a little more difficult to understand, so I'm going to talk about amplitude first instead, okay? So when I'm doing y equals cosine theta, you guys know what's the biggest value that I can get. It's 1. Well, what if I take the result of cosine theta and I multiply it by 2? If my highest value before was 1, what do you think my highest value is now? Hopefully you guessed 2. And notice that when I make it y equals 2 cosine theta, look, my peaks are now at 2 instead of at 1. So if I can change this to anything, 3, 4, 5, whatever number is in front of cosine becomes our amplitude. And it doesn't matter if I like add 2 to this or something like that, okay? That doesn't affect that at all. So this number in front, that affects the amplitude. Why? Because it's taking my maximum and minimum values, which are 1 and -1 for sine and cosine, and multiplying it by whatever is in front of here. Okay, so I think that's not too hard to figure out. The only thing that you have to be careful of is that, remember, that negative doesn't matter. If I make this -5, notice that my peaks and troughs are still at 5 and -5. So a negative here doesn't change amplitude, okay? Oh, that was kind of like sound waves, okay. Y equals, okay. So that's amplitude. Now let's talk about period. Periods looks a little more confusing. It's 2 pi divided by the absolute value of b. So why is that? So let's see what happens when I put a 2 in front of this theta, okay? And I think, okay, just to be clear, these are being considered to be in parentheses by Desmos. So cosine of theta, I'm gonna add a 2 here, and watch what happens to the bumps, okay? In fact, maybe I can zoom in. Nah, yeah, okay, good. And so I put a 2 here, watch the bumps. So what you should have noticed is that the bumps get smaller and more frequent, okay? And what you should think about this is, what we're doing is we're taking our theta and we're multiplying it by 2. Well, what that means is, as we're going through the unit circle, when I get to 90 degrees, I'm actually at 180 degrees. And at 180 degrees, I'm already at 360 degrees. In other words, we are cycling through our unit circle twice as fast. Okay? So if I make this 4, you should see many more bumps. Let's do it. So look at that. Lots of bumps, right? What if I do 180? Oh, that's not what I expected. Let's do 18. Okay, so if I multiply my theta by 18, I'm cycling through the unit circle much faster. If I'm cycling through remember, a period is how many degrees or radians we have to go through before we repeat our unit circle. Well, if I'm going through my degrees faster, then my period is going to be smaller. Okay, so let's take a look at this now. Well, actually, let's do y equals cosine theta, and y equals cosine of 2 theta. I keep forgetting Desmos doesn't care about the backslash. Oh, this looks pretty cool. Woo, aliens. Okay. And lost my train of thought. So for y equals cosine theta, notice, when does it repeat? It repeats at 0, and it repeats at 2 pi. Or rather, I should say it's at 1, at 0 and 2 pi. So how long did it take to repeat? It took, this distance of 2 pi before it repeated. So its period was 2 pi. Well, for cosine of 2 pi, let's see what it's like. Sorry, cosine of 2 theta. Here's 1. Where's my next one? It's at pi. Here's 2 pi, but that's 2 repetitions, right? Here's my peak, trough, peak. It only took pi to get back to my y value being 1. So it took half as much time. So the fact that it took half as much time, that's what leads us to this 2 pi over b. Whatever's in front of theta, you divide 2 pi, which is our normal period. You divide it by this number because that's how fast it's speeding it up. So if I had b equals 2, if I had sine, or let's do cosine of 2 theta, it would be 2 pi divided by 2, which would be pi. And what did we experience? This is pi for its period, right? Okay, so I think that at least it feels to me like a reasonable, adequate explanation of this. So I'll talk about I'll just point to these as examples real quick, and then I think I'll conclude this because I don't think this is too tough. At least that's what I think, and hopefully you guys agree. Where's my I? Oh, there's my I. Okay. So for y equals 3 times sine of 2 theta, you guys know what's the amplitude. It's just this, right? That's what our highest value from sine of 2 theta is 1. We can't go higher than 1. So 1 times 3 gives us 3, and that's the amplitude. That's as high as it can go. And then compared to the midline, sine of 2 theta, this 2 is making us cycle through twice as fast. So we normally cycle every 2 pi, but we're doing twice as fast, so we divide it by 2, and that means it only takes pi to go through once. So that's why our period is pi. Okay, so I think that's a pretty simple example. So let's talk about how you would graph one of these. And on your test, I think you just have to pick the right graph, which isn't hard. Just make a little function table and test a few points. Okay, so y equals 4 times sine of theta. Well, right now, here's my 4, right? And that means the amplitude's 4. There's nothing in front of theta, so my period is 2 pi. And this is wow, that's really hard to see, isn't it? I mean, ugh. Okay. But this is 0. Okay. So if theta is 0, you know sine of 0 is 0. So we'd put this point here. Then you know when theta is pi over 2. This is pi over 2 right here. Okay, and this is 3 pi over 2 right here. This is how I'm reading those. When theta is pi over 2, sine of pi over 2 is 1. And 1 times 4 is 4. So I'd mark this point, pi over 2, 4. Okay? And it'd be fine to, to make, yeah, you can make like a function table like this, if it helps you. Okay, I don't think it's necessary because you're just graphing these points real quick, but let's just do it real quick. So what are some degrees we care about? 0, pi over 2. I'll put a little bar here and we care about pi and 3 pi over 2, and then 2 pi. These are like the values we care about, right? And by care about, I mean they're easy. You guys just learned all of the square root of 3 over 2 and stuff like that. And you can do that if you want for these graphs, but you don't need to. Just pick the easy values, the 1s, the 0s, the -1s. Don't make it hard on yourself. We're not asking you to do anything other than be able to tell us a few things about these graphs right now and graph them accurately. So when theta is 0, sine of 0 is 0. 0 times 4 is 0, so y is 0. When theta is pi over 2, sine of pi over 2 is 1. 1 times 4 is 4. And when theta is pi, sine of pi is 0. 4 times 0 is 0. When theta is 3 pi over 2, sine of 3 pi over 2 is -1. Times 4 is -4. And when theta is 2 pi, sine of 2 pi is 0. 4 times 0 is 0. So we get 0, 0. That's this point right here. Pi over 2, 4. Here's pi over 2, 4. Pi 0. This is pi 0. 3 pi over 2, -4. This is 3 pi over 2, -4. Okay. And 2 pi 0. 2 pi 0. Okay. So that's all you have to do. And obviously you'd want to extend it back, right? If this is a paper test, you'd have to test all these points going back over here. Or what I think is a lot better is to understand period 2 pi, okay? And so you know that if pi over 2 is 4, you can go back 2 pi worth, right? This is going back 2 pi worth. And just mark 4 again. Okay, and same thing over here. Go back 2 pi worth and mark -4 again. And then, like, for me on a test, I would just, you're done. Okay. So I feel like that's pretty easy lesson. I don't really feel that these are just, it's the same thing over and over again. You're just making a function table based on the values and doing some slight alterations. But if you have questions, post in the discussion board and I'll go over more. It seems very straightforward to me going over it right now. So I'll conclude there.